Consider a flat plate at zero angle of attack and an airflow at standard sea level conditions. Now it's given to us that the chord length is 2 meters and the planform area of the plate is 40 meters squared. So now we're also given that the wall temperature is the adiabatic wall temperature T sub AW. This is going to come in handy later for part B. So now what they want us to do is they want us to calculate the friction drag on the plate when the free stream velocity is A, 100 meters per second, and B, 1000 meters per second. So let's start out with part A. So they give us that the free stream velocity is equal to 100 meters per second. Now also at standard sea level conditions, density or rho infinity is 1.225 kilograms per meter cubed. Now this can also be found by using the equation rho infinity is equal to P infinity divided by RT, but we can also use the tables to double check, and we should get theoretically the same value. So now the first thing that we want to do is we want to first check if the velocity that we're currently at is in that incompressible region or that compressible region. Because remember, with laminar flow and with turbulent flow, if we're in that compressible region, we have to use the charts to accurately get our skin friction coefficient. And we'll get into that because in B, just a spoiler, we're going to be in the compressible range. But for A, so we're at a velocity of 100 meters per second, and we can calculate the free stream speed of sound as gamma r t infinity, and that'll be under a square root. So we'll have 1.4, and the gas constant is 287 joules per kilogram Kelvin. And then we'll multiply by the temperature, which was 288 Kelvin. And then we'll take the square root. So then that'll give us a free stream speed of sound of 340.2 meters per second. So now for the free stream Mach number, it's going to be V infinity divided by A infinity, or 100 divided by 340.2. So that'll be a Mach number of about 0.29. So we are right at that edge of 0.3 where we have that transition between compressible and incompressible. So for this problem, we should be safe to assume that we are in the incompressible region. So then the next thing that we need is our Reynolds number. So now the Reynolds number for the full length of the chord is going to be equal to the free stream density times the free stream velocity times the chord length divided by our viscosity or free stream viscosity. So now with this, we can say so 1.225 kilogram per meter cubed. Our velocity is 100 meters per second, and the chord length is 2 meters. And then we can divide by 1.7894 times 10 to the negative 5 kilogram per meter second. So that'll leave us with a Reynolds number of about 1.36 times 10 to the 7. So then what we can do with that is now we can calculate the coefficient of skin friction drag, or C sub F. So now for laminar flow, we have two different versions. We have the local version and we have the full total version of your entire wing. Now we want to use the entire wing where we're going across the entire chord length. And that would be 1.328 divided by the square root of the Reynolds number for the chord. So we can essentially just plug in the Reynolds number that we just calculated. So we'll have 1.328 divided by the square root of 1.36 times 10 to the 7. So then that'll give a coefficient of skin friction drag of 3.6 times 10 to the negative 4. Okay, so the next thing that we need to do is calculate the skin friction drag. So that is equal to 1/2 rho infinity V infinity squared times the surface area times the coefficient of skin friction drag. So we can just plug in our values from before, so I'll do that real quick. Okay, and that'll leave us with a skin friction drag of about 87.8 newtons. But now that is not our total skin friction drag, because we actually have to multiply by 2 to account for both the top and the bottom of the wing. So we can do 2 times d sub f. So that'll give a final skin friction drag total of 175.6 newtons. And that is the end of part A. So now for part B, we are at a free stream velocity of about 1,000 meters per second. So that's pretty darn fast. Now we're going to have the same free stream speed of sound. So it's going to be 340.2 because our temperature hasn't changed and gamma and the gas constant haven't changed either. So then we can calculate the new free stream Mach number. So that's going to be V infinity divided by A infinity. So we'll have 1,000 divided by 340.2, and that'll equal about 2.94. So we are way outside of the incompressible region, and we are in the supersonic region of travel. So we can no longer assume that we are in incompressible flow. So now what we'll have to do is we'll actually have to use this chart down here. So the way this works is we have our essentially Mach number down here, and then we have the coefficient of skin friction drag times essentially the square root of the Reynolds number along the full chord length. And pretty much what we're doing is we have our Mach number of 2.9, so we can try to find that on the graph down here. Let me grab my pen, and then we'll essentially trace it up. But now notice we have two different lines here, and the question is which one do we go to? But in the problem statement, it told us to assume that the temperature of the wall was the adiabatic wall. So what we can do is we can draw this line up to this first line here. So about right there. So that is roughly about 1.2, give or take. So what we can then say is that the CF times the square root of Reynolds number C is going to be about 1.2. So we can essentially just approximate it. Actually, let me move this back a little bit. So then we can write that CF is equal to 1.2 divided by square root of Reynolds number times C. So we can set that equal to 1.2 and then square root. We can actually do a little sneaky trick here. So we don't have to recalculate Reynolds number because notice from before, Reynolds number, so we have density, that didn't change. We have chord length, that didn't change. Our temperature didn't change, so our viscosity better not have changed. But for our free stream velocity, that actually increased by a factor of 10. So our Reynolds number, we can simply say that's a factor of 10 greater than before. So we'll have 1.36 times 10 to the 8 now for our Reynolds number. 1.36 times 10 to the 8. So that'll leave us with a coefficient of skin friction drag of 1.03 times 10 to the negative 4. And then with this, we can calculate our skin friction drag once again. So we'll have 1/2 V infinity squared, and CF. So let's go through, write all the values out again. Only this time, so we'll have 1,000 meters a second for V infinity. And that'll give a drag for one part, or like one surface of the wing, as 2,513 newtons. So now what we can do is calculate what D total will be. So DF total is going to be twice the skin friction drag, so we have to account for both the top and the bottom of the wing. And that will be, here, so let's write this out, so we get D total. That'll be about 5,026 newtons. And see, I really like this problem because I feel like it's a good way to show how drastically different the drag would be if you're looking at compressible or incompressible drag. And now with the next example that we'll end up doing is we'll actually look at turbulent flow to see if we take basically the same exact example, except we just do turbulent flow instead, how would that differ? And it's quite interesting seeing how large the turbulent flow is compared to the laminar, because you have all those viscous effects essentially happening along the surface. You have a much more added drag, and you have to deal with a lot of that, especially when designing aircraft. So it's definitely a good example to go over, kind of learn from, and I'll see you next time.